In this video, I want to talk about model calibration. This is a very crucial but often overlooked topic, in my opinion. Calibrating probabilities means that we can then directly interpret those probabilities as confidence levels. So whenever our model predicts the positive class with a 40% probability, that actually means 40%. So this may sound a little bit confusing, but out of the box, most machine learning models don't have directly interpretable predicted probabilities. There are idiosyncrasies in these models to where if something is predicted 40% of the time, it may not actually happen 40% of the time. It may happen 35% of the time or 47% of the time. It's because these models are not calibrated under the hood. Now, something like logistic regression actually is fairly well calibrated just in and of itself, but most tree-based models have idiosyncrasies in these predicted probabilities. And so I will link to this chapter here in a handbook that I wrote that talks more and more about this, and we'll also reference this later on in the video. But one specific example that's pretty well known is that something like a random forest tends to push probabilities towards the middle of the distribution, and they are less likely to predict probabilities at the extreme ends of the distribution. And if you think intuitively about random forests, this makes sense because due to the ensemble of trees, those help prevent overfitting. They kind of hedge the model a little bit. Scikit-learn also has some really good documentation on probability calibration. I would definitely recommend reading through this, and you can kind of see what's called a calibration curve here. So your perfectly calibrated model should fall along this identity line here, but you can see that here are some different models, and yeah, those are not falling on the identity line. They do have kind of these idiosyncrasies to them. So even though a model may not be well calibrated, the cardinality of the predictions may be valid. So you may be able to still rank order the predictions, but that doesn't necessarily mean that the rank order of predictions is indicative of a direct probability. So this can sometimes be a little bit confusing, and we'll get into this slightly more, but something like a lift chart or a cumulative gains chart, that helps measure cardinality of predictions. That does not help measure calibration. So again, with calibration, we want something that's going to fall right on this identity line in a perfect world, and we can see that the logistic model here in green is actually pretty well calibrated. More so than the other models as well. So this is something that is really important. Again, at the end of the day, machine learning models are just tools to accomplish business goals. So let's say that person A has a 2% probability of canceling their subscription, and person B has a 47% probability of canceling their subscription. I'm pulling this kind of from this part of the text here. Even though those are both in the negative class, we would probably want to treat those people differently with some type of a real world application. One has virtually no chance of canceling their subscription. Another is more or less a toss-up. So again, most of the time, in my opinion, when we're building real world classification models, we care about the predicted probability, because somebody who has a 2% chance and somebody who has a 48% chance, even though they're both under 50%, we want to treat those people differently. And when we have well-calibrated probabilities that can be directly interpreted as confidence levels, we can do things like that. The flip side is also valid. Somebody who has a 55% chance of canceling should be treated differently than somebody who has a 90% chance of canceling. So again, what we're trying to do with machine learning is not just predict numbers, it is to enable some type of action. So let's actually take a look at some code here. I have a main function that will just load some data. This is classification toy data from scikit-learn. And then we're going to train every model in model training list. And in this case, this is just one model, but this is a way that you can kind of take the frameworks we've been using and quickly iterate over different models so that we don't have to write a bunch of boilerplate code. So we iterate over everything in model training list, and then we train our model with HyperOpt. You've seen that before. And then we do some calibration slash cardinality checks on our model. So let's kind of walk through what's going on here. So first, let's look at model training list. So this is just a named tuple. I like this methodology because I can reference specific attributes that I have come up with different nomenclature for. So you can dig a little bit more into what this code is, but this is a random forest. And how do I actually calibrate my model? So if you saw in the scikit-learn documentation, it provides calibration curves, and it also provides something called a calibrated classifier CV. You may not have actually seen that because I wasn't on the web page for very long, but how you can actually calibrate your model is with this calibrated classifier CV, and I'll jump back into what that is back on the web page here in a moment. But you can say, all right, I want the calibrated classifier CV, and then I want my estimator that will be calibrated as a random forest classifier. And then for the parameter grid, you can see that this is a little bit different, that we are tuning the estimator, and these are the parameters of the estimator. So this used to be called base estimator in older versions of scikit-learn. It's now just called estimator. But you can see that we need to set up our parameter grid a little bit differently to actually tune the estimators of the random forest. So calibrated classifier CV is one way that you can get calibrated probabilities, or at least train a model that is trying to get calibrated probabilities. The other way you can do that is you train your model like normal, and then you calibrate it on a holdout set. So that is another valid way. We're not going to go over that specific methodology, but back in this web page, you can see that there's actually some documentation on how you would actually do kind of the post hoc calibration. So yeah, that's actually kind of defined here in this bullet point here. We create a validation set from either our training data or our testing data. In such an instance, we would have training, validation, and testing sets. We would train on our training set, calibrate on our validation set, and test on our testing set. So that's one way to do that. The way that I like is with the calibrated classifier CV. So this is actually a pretty complex model. There's a little visual here that walks you through exactly what's going on under the hood, but more or less, you can think of it as we're training our model, and then we're also training a calibrator on top of our model. So basically what will happen is the random forest will predict the probabilities, and then we will train a separate calibrator model to go in, and then based on some holdout data, get feedback on how do I actually better calibrate these probabilities. So you're training these actual like model pairs, if you will. So your estimator and then a calibrator model to go on top of that. And then this kind of all goes into an ensemble. There's, again, a lot going on here, and I think it's probably best for the listener to actually go in and look at this documentation and read through exactly what is happening here. And then, of course, I also mentioned this previously, but you can see how they actually do some post hoc calibration on a validation set as well. But kind of the main point that I want is that you can't just hope that a random forest will be well calibrated out of the box. You actually have to use calibrated classifier CV or do calibration on your validation set. And you're still able to use calibrated classifier CV for that as well. That is still what you use, but it's whether or not you use it in nested cross-validation when you're optimizing hyperparameters, or if you do it post hoc. So I like to do it when I'm training my hyperparameters because, for example, the best max depth that's calibrated well may be different than if I did post hoc calibration. So in another way, the max depth that I want to choose could be influenced by my calibration process. So to produce the best holdout results on the whole, I find that I can get a nice interaction between calibrated classifier CV and max depth, and I want those two things to interact in nested cross-validation. I know that's a little bit tricky, but again, I think if you read the web page, maybe that will sink in a little bit more. So we train our calibrated classifier CV. we produce a predictions data frame, and then we produce something called probability lift. So this is actually something that I kind of came up with, and this is an implementation for that. So I'm actually just going to kind of read the doc string for this. So this function calculates the lift of the probability estimates. Lift is determined by how much improvement is experienced by using the predicted probabilities over assuming that each observation has the same probability of being in the positive class. So basically what this function does is it finds the overall rate of occurrence of the positive class. It cuts the probability estimates into n bins, which is a default of 10, but we can override that. For each bin, we calculate the average predicted probability and the actual probability. For each bin, we also then calculate the difference between the average predicted probability and the true probability, and the difference between the overall rate of occurrence and the true probability. We take the sum of the absolute values for each difference, and then we take the ratio of the two sums. So again, I know there's a lot going on here. I'm kind of running through this more quickly than I probably should just to introduce these topics, but the idea is that we want to quantify how much does our model improve by actually having calibrated probabilities as opposed to just assuming that everybody has the overall rate in the data set. And so this is one way to do that. This isn't a perfect way or the only way to do it, but it's one way that I've kind of come up with to basically say if we came up with these different discrete spaces of our predicted probabilities, how much better are we in each of those bins by using what the model said as opposed to just assuming some type of a rate uniformly across all observations. Then we plot the calibration curves. So we saw those briefly in the scikit-learn documentation, and also in this web page, there's documentation on that as well. But we can basically reproduce these plots here. These are very, very good for visually inspecting the model calibration. So there can be some idiosyncrasies, obviously, when you're trying to eyeball something. It's not as exact as getting a specific number. That's why I like the probability score, the probability lift, I should say, that I mentioned above, because that's something that is a little bit more directly interpretable, but calibration curves are really useful as well. There are two main binning strategies. So one is uniform. All bins have the same width, and then quantile. So bins have the same number of observations. So generally you want to look at both if you can, but kind of depending on your use case based on the overall prediction space, one or the other may be more informative. And again, we will kind of look at what this actually does in practice, but you can pass in what type of binning strategy you want, and you can view that in the documentation to get more information on what those strategies mean. And then we also plot cumulative gains and not cumulative, but lift curves. So the reason I plot those is because some people think that those mean calibration, but again, those just mean that I have the right cardinality of prediction. So you could have great lift with your model and not necessarily have great calibration. So let's say that you were able to very, very confidently predict a certain part of the distribution that could give you great lift with certain areas, but if the model tanked on others and was really poorly calibrated, then your lift would suffer, but it might be outweighed by great lift in other areas. So that's a little bit nuanced, but I wanted to just kind of plot these out to show that those don't actually measure calibration. Those measure that you have predictions with the right cardinality, if that makes sense. And I have also included some links to explanations of what those charts mean. They can, even for me, and I've been doing this for many years, it can be when I'm looking at those charts like, what exactly is going on? But they are fairly intuitive if you look at some documentation. So again, kind of the main idea is that at 50% of customers contacted in this case, that I could get 85% of the people that I actually need to talk to that would actually be in the positive class. So you're getting some nice lift, which means that you have good cardinality in your prediction. So if your model wasn't actually that useful, if you weren't getting any lift, it would just fall kind of along this identity line as well. And then the lift chart is just basically another representation of that. So basically here, this is saying that at your greatest lift, you're getting like a 3x improvement based on the highest predicted probabilities. So again, that's cardinality and not calibration. So let's run this bad boy. So we can see that our loss improved a little bit, and that spit out a bunch of files. So of course we have our pickle file, we have our cross-validation scores. Let's look at our lift score. So I think that gets popped out in a CSV file here. So our lift is 12. So this is saying that we get a 12x lift by using the model's predicted probabilities, as opposed to just assuming that everybody has the exact same probability, which is just the overall rate of occurrence of the positive class. In a certain way, this is how we can quantify the calibration curves. It's not an exact translation, but it's the best that I could come up with to actually put a number on these calibration curves. So let's look at the calibration curves. I also save the CSVs of just the raw data on these as well. I think that's useful. Let's look at the quantile plot, and let me go back up to the documentation. So quantile, all bins have the same number of observations. So this created, it looks like about, it should have created 10 bins. But you can see that, this is falling along the identity line, but we're seeing some bins that have, basically kind of some wonky calibration here, some wonky calibration up here, but we can see that kind of in this middle bin. Again, this would have the same number of observations as this, that we get something that's pretty well along the identity line. So this one's a little bit weird because it looks like the probabilities are either kind of globbed towards very close to 0, very close to 1, or smack dab in the middle. But if you were to apply a different data set, this would look a little bit different. Let's look at the uniform calibration plot. So this ensures that we have the same spacing. So one of the issues is that there could be very, very few observations in some of these bins. Whereas again, with this one here, every bin is guaranteed to have the same number of observations, but we can see that these are not by any means evenly spaced. But this is going to have even spacing, so we can see our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are all evenly spaced. And we can see that this bounces around quite a bit. But again, it could be the case that some of these have like very, very few observations in them. So that could be one of the reasons for the noise. But just looking at this in and of itself, yeah, it bounces around a lot, but we can see that, at certain parts of the distribution, okay, we are doing pretty well once we get above the 70% mark. We are seeing here at the bottom part of the distribution that we do see things that are off the identity line, but we see things kind of spike up and make a little bit more sense, but again, pretty noisy, so not necessarily the best calibrated model. I think this is probably just because of the data and the fact that we probably only ran, 15 optimization trials, but this kind of, again, is just a diagnostic to help us look at the model in addition to a bunch of other items that we want to look at for calibration. So think of this as a portfolio of ways to look at calibration, because there's not necessarily as intuitive of a direct way to look at calibration. One other thing that I want to note is that whenever we want well-calibrated models, we should use probably negative log loss, or if we're doing this not in cross-validation, if we're just using this in plain like evaluation of scikit-learn, it's just called log loss. So that is probably the best loss function to get well-calibrated probabilities, because those penalize predictions that are confident but wrong. Breyer score is another one that's good. But if we want really well-calibrated probabilities, we actually don't want to use something like F1 score or ROC-OCK. ROC-OCK is good for cardinality of predictions. F1 is really just good for class labels. Again, I would submit that we almost never really care about the class label. We care about the probability that we can then bin up and turn potentially into multiple class labels. So again, if something's in the positive class at 51%, we want to treat that differently than something at 90%. So log loss is typically my go-to for any classification problem. Again, I'm just going to kind of gloss over the cumulative gains and lift curve, because this video is at this point running quite long and I've already covered those a little bit. But again, these are, again, just looking at cardinality and not necessarily calibration. So we could have predictions that have perfect or near perfect cardinality to them, but they're not still directly interpretable as confidence levels. So we can see that we are getting great lift out of this model above our baseline. With our highest predicted probabilities in this space, we are getting great lift over the baseline. So we have good cardinality, but that doesn't necessarily back into great calibration. So those are two separate concepts. I know I've been driving that home a lot, but that's, definitely illustrated by this example where we have actually not that great calibration if we look at the metrics, but we have some decent performance in the lift charts. I know this is getting long, but a couple other things that I will mention at the very end is that there is no objective good log loss. It is all relative. So one log loss can be compared to the other, but they don't have any meaning in an absolute sense, like ROC-OCK or F1 score. So log loss can really only mean something in relative sense. So, we may say, oh, this looks like a good log loss, but it doesn't really mean anything. But we can look at the calibration curves to get a sense for how well this is calibrated. This looks a little so-so to me, but again, there could be some issues where there's just small sample size in certain parts of the prediction space, and so that causes the noise. And that's something that if we were doing this for like an actual case, an actual problem, we would look more into that and say, okay, the reason that this uniform calibration looks kind of weird is just because we are seeing some like really small sample sizes in, like, for example, this bin or this bin here, so we should throw that out or something along those lines. The last thing I'll mention is that the probability lift, so again, this returns something like a 12x improvement, and again, that is mostly relative. We can look at that a bit in an absolute sense and say, okay, we're getting 5x or 10x lift, but again, this is really kind of dependent on the problem itself. In certain problems, we may expect great lift. In others, we may expect small lift. So just because a probability lift looks good in and of itself doesn't actually mean anything. It could just be the case that, for example, we're dealing with something that's very, very imbalanced. So we might get great lift if, we're producing probabilities of, like 5 or 10% being in the positive classes. This is like fraud detection. But that may still be very insufficient for our application at hand. So again, this lift score can be useful, but it's mostly used for relative comparison and not necessarily absolute comparison. All right, that was a lot of information. Thank you for bearing with me, and I hope you've learned a lot about calibration.